Good morning, students. Today we are going to discuss upon the complexity of recursive algorithms. Before going into the discussions on complexity of recursive algorithm, let us discuss the types of algorithms. Algorithms can be classified into iterative as well as recursive algorithms. Iterative algorithms are written using loops and the flow is sequential. Whereas in the case of recursive algorithms, a function is calling itself with different parameters or values of n. Iterative algorithms can be converted into recursive algorithms. Now, coming to the analysis part, iterative algorithms are purely based on the number of times a loop is executed, whereas in the case of recursive algorithms, they are based on the evaluations upon the recursive equations. Now, even though they are implemented using different ways, the power of both the iterative algorithms and recursive algorithms are the same, as they can be converted into from one to the another. Now, let us discuss how to compute the complexity of recursive algorithms. For computing the complexity, there are three methods, starting with the back substitution, recursive tree, and master's theorem. For the same, let us discuss the brief example. Given a small code snippet wherein which a function is calling itself with a value n by 2, and this function invocation has been invoked 2 times. So here our main objective is to first derive the recursive equation for this particular code snippet. Okay, so here assuming that t of n represents the time complexity of this function, okay, this statement, if statement, will be executed with a constant time. Now coming to the two recursive calls which are there in this if statement, okay, the time complexity of the function call where n is equal to n by 2, okay, the time complexity we can assume that it is t of n by 2. Since there are two calls, we can write it as 2 times t of n by 2. Now the recurrence relation or recurrence equation corresponding to this code snippet can be written as t of n is equal to c plus 2 times t of n by 2. Now let us consider the second example. Okay, here there is a code snippet. Here there is a code snippet a of n. Okay, this function is being invoked within this code snippet with a recursive call of a of n minus 1. So we can write the recurrence relation to this code snippet as t of n is equal to t of n minus 1 plus 1. Now let us discuss another example. So here in this example we can see that the code snippet is invoking the same function in 2 times, okay, with a value of n is equal to n minus 1. So here again we can write the recurrence relation as t of n is equal to 2 times t of n minus 1 plus 1. Now to make our recurrence relation more precise, we can see that t of n is equal to 2 times t of n minus 1 plus 1 when the value of n is greater than 0 and t of n is equal to 1 when n is equal to 0. Now let us solve this recurrence relation using the first method, that is back substitution. So here we'll consider the equation of t of n, which is 2 times t of n minus 1 plus 1. So when we substitute t of n minus 1, okay, so here we can see that it is 2 times 2tn minus 2 plus 1 plus, so this is the representation for t of n minus 1. We substituted this as follows. Now we'll retain the remaining part of the equation as it is. This can be written as 2 square times t of n minus 2 plus 2 plus 1. This is our second equation. Okay, further our objective is to solve this equation. So we'll try to replace this t of n minus 2 as follows, that is 2 times t of n minus 3 plus 1. Hence the recurrence relation here can be rewritten as, this equation can be written as 2 raised to 3 times t of n minus 3 plus 4 plus 2 plus 1. So on and so forth. This can be substituted, assuming that there are k times we are substituting it. Okay, so after k iterations, you can see that the equation turns to t of n is equal to 2 raised to k times t of n minus k plus 2 raised to k minus 1 plus 2 raised to k minus 2, etc. plus 2 raised to 2 plus 2 plus 1. Now, from this code snippet, it's very clear that the terminating condition is when the value goes to when n minus k is equal to 0. That is t of 0. When the value of t of 0, this t of n will reaches a value of 1. Okay, so since the terminating condition here is n minus k, so this should go to 0. This value should go to 0. N minus 1 is equal to 0. N minus k is equal to 0. That means n is equal to k. Okay, so here we are substituting when n is equal to k. In this given equation, we get t of n is equal to 2 raised to n times t of 0 plus we are writing the remaining part of the equation in terms of n. When after writing this, we can observe that it is a geometric series, okay, of the form a plus ar square plus etc. plus ar raised to k. The solution for this equation, this series, is a times r raised to k plus 1 minus 1 by r minus 1. Here a is equal to, in this given equation, we know that a is equal to 1 and r is equal to 2. So when we substitute it, we get the value of this part as 2 raised to k plus 1 minus 1. Here, substituting the values in this given equation, we get t of n is equal to 2 raised to n plus 2 raised to n minus 1, that is equal to 2 raised to n plus 1 minus 1. So here, the complexity of this code snippet can be written as big O of 2 raised to n square, 2 raised to n. Now, let us solve the same equation, recurrence relation, okay, using the recursive tree. In the recursive tree, we are going to draw recursive tree method. We are going to represent it as a tree in the tree form. T of n is invoking itself 2 times plus a constant time is associated here. So we write it as, there are three branches to this t of n. 1, then t of n minus 1, that is the first invocation. The second invocation is t of n minus 1 again. Now this t of n minus 1 can be represented as 1 and t of n minus 2 and another t of n minus 2. Likewise, we can expand this tree, okay, and this will continue till the value of t, till the value of n goes to 0. That means in this tree we can see that, okay, in this tree we can expand this tree till the value of n goes to 0. Now we are trying to compute the complexity of this recurrence relation. So our main objective is to find out the total work done. Now for that we need to compute the work done at each level. Now the work done at the level 1, okay, the level 1 is 1 unit, okay. This is the it's the 0th level. So this is 0th level. The work done is equal to 2 raised to 0, that is equal to 1. At the first level, okay, this is the level 1. So here the unit of work done is equal to 2. Okay, proceeding further, here we can see the work done is associated with the expansion of these 4 function invocations. So the work done is equal to 2 raised to 2, that is equal to 4, so on and so forth. Okay, at the kth level, we can find that the work done is equal to 2 raised to k. So the total work done is a summation of all these values together, right? So we can rewrite it as 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2, etc. to 2 raised to k. This is equal to 2 raised to k plus 1 minus 1. Okay, now what is t of n? T of n is here 2 raised to n plus 1 minus 1. We know that n is equal to this expansion of the tree will continue till n is equal to k, right? And we know that the number of levels is equal to k, which is equal to n. So t of n is written as 2 raised to n plus 1 minus 1. Hence, the time complexity or T of n can be written as theta of 2 raised to n.